Alright, so today we're still finding limits algebraically. This is day 2. And so we talked in the previous lesson about using direct substitution, and if that yielded a valid number, then that was the value of the limit. We had some examples where we had 0 over 0 when we plugged in, and we said that that was called the indeterminate form. Today we're going to look at some examples of what happens if when I plug in I get some numeric value divided by 0. Not 0 over 0, but some numeric value divided by 0. And so what usually happens in this case is that if you think about it graphically, what you have is a vertical asymptote at whatever x value your limit is approaching. And so either your graph is heading up infinitely on both sides. Perhaps it's heading down infinitely on both sides. Or it could be that on one side it's heading up and on the other side it's heading down. So if both sides of the graph on either side of that point are heading upwards, then we talk about the limit being infinity. If both of them are heading down, the limit is negative infinity. But if one is going up and one is going down, that's where the limit from the left and the limit from the right aren't equal, and therefore the full limit does not exist. So when you plug in to evaluate a limit and you get some numeric value divided by 0, you have to test the left-hand limit and the right-hand limit. So you want to test a number that's very close to that value. So if your limit is as x approaches 2, then you would want to choose a number just to the left of 2, like 1.9, and just to the right of 2, like 2.1. And when you plug in and you look at your y value, you're either going to get a positive result or a negative result. Positive just means that as you're approaching from this side, your graph is heading upwards. A negative result says if as you're approaching from that side, your graph is heading downwards. And so you're looking for either both positive, both negative, or opposite signs. And so once again, if the signs aren't the same on the left and the right, then that limit does not exist. Then we're also going to look at some examples of piecewise functions where we're finding the limit as x approaches the value where that piecewise function splits. And in that case, you have to look at the one-sided limits. You've got to look from the left and from the right and see if they are the same. In other words, when you sketch your piecewise function, if 2 is where the function splits, if one of them comes up here and then it jumps down and goes the other direction, so you've got this big gap in your graph, then the limit would not exist. But if you're looking at, say, a point right here and your two functions meet at the same point, then that's going to be your limit. And so you're looking at coming from the left and from the right with a piecewise function as well. So on our first example, we've got very basic, the limit as x approaches 0 of 1 over x. And so when you plug in, you get 1 over 0. Once again, any number divided by 0, we need to test to the left and to the right of this value that we're approaching with our x's. So make yourself a little table of values. We're approaching from the left of 0, which would be negative 0.1. We want to approach from the right of 0, which would be positive 0.1. And so when I plug in a negative 0.1 or a negative 1/10, 1 over negative 0.1, I get a negative result. I don't really care what the number value is. All I care is if it's positive or negative. If I plug in a positive 0.1, I get a positive result. Once again, I don't really care what the actual value is. All I care is it positive or is it negative? And so I look at these results on the left and the right. If they are not both positive and not both negative, then my limit does not exist. And if you're asked to tell why, the reason is because, BC means because, the limit as x approaches 0 from the left is not equal to the limit as x approaches 0 from the right. should say, of 1 over x. Okay, the reason is because the limit as x approaches 0 from the left of 1 over x is not equal to the limit as x approaches 0 from the right of 1 over x. Okay, look at the next one. I'm approaching 4 this time, so plugging in a 4 in the numerator. 4 minus 4 squared in the denominator gives me 4 over 0 again, which means I have to test on the left and the right of this 4. And so 3.9 is on the left, 4.1 is to the right. So if I plug in a 3.9, notice in the numerator I've got positive, in the denominator it's squared, so it's always going to be positive. So my result, positive divided by positive, is positive. If I plug in a 4.1, the numerator is positive, the denominator is squared, so it's always positive. Positive divided by positive is positive again. So because these are both positive, that tells me that my limit is going to be positive infinity. Okay, if they had both been negative, then it would have been negative infinity. But they're both positive, so it's positive infinity. Let's look at C. Notice, be very careful. What are you looking at here? This one only wants the limit as you're approaching from the left. It's not asking for the full limit. It just wants the limit as x approaches 2 coming from the left. So if you plugged in the 2, you get 1 over 0, which tells you once again that's where there's a vertical asymptote. So I really only care about plugging a number in that's just to the left of 2, like 1.9. So 1 over 1.9 minus 2 gives me 1 over negative 1/10, which is negative. That tells me that my graph coming from the left is heading downwards towards negative numbers. So my limit then is going to be negative infinity. D is the same situation. We're only concerned about the limit as I'm coming from the right. So only coming from the right, but when I plug in the negative 1, I still want to always try to plug in first, regardless of whether or not I'm just coming from one side. So I'm going to get negative 6 over 0. So I'm looking at just to the left of negative 1, which would be negative 0.9. So if I plug in a negative 0.9, in the numerator I get negative, in the denominator it's squared, so it's always positive. So I get a negative result because negative divided by positive is negative. So my limit then is going to be negative infinity. Let's look at some examples of the piecewise functions. So the first piecewise function, f of x is equal to negative x plus 2 only when x is less than 1. It's equal to x squared when x is greater than or equal to 1. So the first one says find the limit only coming from the left. So if you were to graph this, where x is equal to 1 is your dividing point, you've got a negative x plus 2, the slope of negative 1 going through 2, and to the right it's x squared, parabola. So coming from the left, I'm going to plug the 1 into the equation that is to the left of 1. So 1, or negative x is negative 1 plus 2 equals positive 1. So my limit is a positive 1. Now I'm talking about coming from the right. So this is the function that comes from the right, the x squared. So I'm going to plug a 1 into the x squared and I get a 1. So the limit coming from the right is 1. So if I want the full limit, notice there's no plus or minus this time. I want the full limit. I need to explore the limit from the left and the limit from the right. Because they were both the same value, that makes the full limit equal to that value as well. If they had been different values, then that limit would not have existed. So the last example, another piecewise function, 2 minus x only when x is less than -1, and then x plus 3 squared only when x is greater than or equal to -1. All this says is find the limit as x approaches -1. It doesn't tell you to find it from the left and from the right, but in order to evaluate the limit at this dividing point for a piecewise function, you have to investigate the limit from the left and then limit from the right. Even if it didn't ask you to, you have to look at those. So the limit as x approaches -1 from the left of f of x. So here's from the left, so 2 minus -1 gives me 3. I have to explore from the right, so the limit as x approaches -1 from the right of f of x. So the second equation is coming from the right. So I'm putting a -1 in place of x, and I get 2 squared or 4. If I want the full limit, the limit as x approaches -1 of f of x, I look at the limit from the left and the limit from the right, and I compare them. If they are not the same, then this limit, what we call the full limit, does not exist, because the limit as x approaches -1 from the left of f of x is not equal to the limit as x approaches -1 from the right of f of x. So for piecewise functions, if you're looking at the limit as x is approaching the number where that graph splits, that's the key. It's at the point where the graph splits. If it's not where the graph splits, then all you have to do is plug in. But if it's at the point where the graph splits, you have to look at what happens from the left and what happens from the right, and then compare the results.